So we're going to be moving on and taking a look at probability generating functions. A probability generating function is a polynomial which actually stores all the information that you would have in a discrete random variable. Most people don't anticipate being able to represent a discrete random variable as a polynomial, but we'll take a look at how it's done. We're going to make use of the probability itself, and we're going to have a variable, a dummy variable, which is going to be t to the power of x. As you can see from the definition below, for each outcome of the discrete random variable, we're going to find the product of its probability and the dummy variable, and we're going to sum each of those products together. Let's have a look at an example so you can see exactly how this will work. So the notation here we'll use, I'll refer to as gx of t. So that's the generating function for the x variable. I'll start with the outcome 0. So I'll take its probability, 0.2, and I'll multiply it by the dummy variable, which would be t to the power of 0. I'll do the same for the outcome 1. So I have the probability 0.8 multiplied by the dummy variable t to the power of 1. I can do a similar thing for gy of t, and I'm going to take the probability as the coefficient and t to the power of 1. Probability and t to the power of 2, and once again the probability and t to the power of 4. And this is the probability generating function for these two discrete random variables. Now, there are numerous benefits to having our discrete random variable in a polynomial form, to representing our discrete random variable as a probability generating function. As a polynomial, there's so many things that we can do to manipulate them. We can differentiate and integrate, we can multiply, we can add them together. There's so much functionality and utility from being in a polynomial form. So just as an example, I'll demonstrate what we can get from multiplying probability generating functions together. Well, here I can get the probability generating function that I would get from adding these two distributions together just by multiplying their polynomials. And multiplying polynomials is something you've been doing in pure maths for quite some time. I'll start with the 0.2 and I'll multiply that with the whole of that second bracket. So we get 0.02 t plus 0.14 t squared. I don't have any t cubed, so I like to leave a space here. And then I'm going to add on 0.04 t to the power of 4. So that's 0.2 multiplied by the second bracket. Now I'll go for 0.8 t multiplied by the second bracket, leaving the correct spacing so that I can sum these together afterwards. So once again I get three terms. There's no t to the power of 4 term, so I have 0.16 t to the power of 5. Okay, so from here I'm just going to add together the like terms. This was the reason I laid it out like this, to make the summation a little bit easier. 0.02 t plus 0.22 t squared plus 0.56 t cubed plus 0.04 t to the power of 4 and 0.16 t to the power of 5. And that would be the probability generating function for a combination of the two discrete random variables that we had to begin with. Well, how else might we have approached that problem? We could have made a sample space diagram for the two distributions, and we found all of the scores we would get from adding them together. And then we would need to find the probability associated with each of those individual outcomes. So 0.02, 0.14, 0.04, 0.08, 0.56, and 0.16. We could have found all of those in this sample space diagram. And then we would have had to actually produce the distribution for x plus y by combining any of the outcomes that were the same, or combining the probabilities for any of the outcomes that were the same. And then from there, we could have turned that distribution into a probability generating function of its own. And actually, if you notice, we end up with the same coefficients. We have the same probabilities leading to the same coefficients and the same powers of t. So I hope you could see some parallels between the two different ways of me generating the probability generating function there. And it's potentially debatable about which of them is the best one to use, which of those is the most efficient or the most intuitive, but ultimately we want to have more than one way to approach this kind of problem. We want to be able to convert from one form to another, which I know you've seen in so many times in maths is a useful ability to be able to convert from one form to another and then make use of the skill base within that form. Make use of the functionality that form has in it. Okay, so here's two discrete random variables. You might want to have a go at these yourself. How will we generate the probability generating function? The probabilities will become the coefficients and the outcomes will become the powers of t. So for this first one, I'll have 0.6 t to the 0 plus 0.3 t squared plus 0.1 t to the 4. In the second one, I'll have 0.1 t to the 0 plus 0.3 t to the 1 plus 0.4 t squared plus 0.2 t cubed. While I have these both on the screen, there are some things we should be able to recognize. In the discrete random variable, we would be able to know that there was some sort of error, or we would know that it was invalid if any of the probabilities were negative. We would also know there was an error, or if it was invalid, if the sum of the probabilities did not add up to 1. Well, in the probability generating function form, the probabilities are coefficients. So similarly, the coefficients should all be positive, and the coefficients should all add up to 1. Some other limitations of a probability generating function are that we need to have integer values for the outcomes, and they need to be non-negative integers. So non-negative integers for the outcomes, all of the probabilities should be positive, and all of the probabilities should add up to 1. Meaning all of the coefficients are positive and all of the coefficients will add up to 1. Well, that's really how you recognize if you have a valid probability generating function. But let's go through some more formal properties of a probability generating function. Well, firstly, let's consider this probability generating function. What would I get if I substituted t for 1? So gx of 1, and I substituted a 1 everywhere that I had a t. So I would have a 1 squared, and a 1 to the power of 4 in these brackets. And we know that no matter what power I have applied to a 1, it still gives me the value of 1. So I basically have each of the coefficients multiplied by 1 and added together. And just as we saw informally, the coefficients will always add up to 1. So here we can see that the gx of 1 will always equal 1. Okay, so be careful, hold on to that, make use of that as it is appropriate. Okay, with a discrete random variable, we would regularly find the expectation. So let's go ahead and find the expectation here. I can find the expectation of x. It's going to be the x value multiplied by the probability. X value multiplied by the probability. Do that for all of the x values. And we get 2.3 in this case. What about the expectation of x squared? I'll take the x value and I'll square it and then multiply by the probability. And I'll do that for each of the corresponding x's and probabilities. And in this case, we get 6.1. What would I get if I did the expectation of t to the power of x? Well, I'll take the probability and multiply it by t to the outcome's power. So t to the power of 2 multiplied by the probability. T to the power of 4 multiplied by the probability. And I hope you can recognize this already. If not, I'll rewrite it in a different form. But this is, indeed, the probability generating function for that discrete random variable. So formally, the generating function will always equal the expectation of t to the power of x. Okay, here in this example, we've been told that x is a discrete random variable that denotes the absolute difference of the scores when two fair dice are thrown. We're asked to construct the probability distribution and to write down the probability generating function. So the first step actually would be to produce a sample space diagram, which I've put for you on the screen. And here's all the absolute differences between the scores you would get on the dice. So from here we can produce the distribution. There were 6 occurrences of a score of 0, 10 of a score of 1, 8 of a score of 2, 6 for a score of 3, 4 and 2 for a score of 4 and 5. So this is the probability distribution, and from here we would be expected to then produce the probability generating function. Probability multiplied by t to the power of the outcome. Probability multiplied by t to the power of the score. And we'll do that until we have the entire probability generating function. At this point, I would probably simplify, but while it's unsimplified, we have the opportunity to check that they do actually add up to 1. So just adding those numerators, we should get 36. So a quick sense check to make sure we do have the correct probability generating function. So a throwback to year 12 by asking you to produce that sample space diagram and then using that to produce the discrete random variable, and from there we've turned it into a probability generating function. Well, in this next example, we're told that the generating function is as shown on screen and we're asked to find the value of k. Well, we're going to use the property that we know the generating function with 1 substituted in will give us an answer of 1. So let's go ahead and substitute in 1, expand those brackets. We're going to get 2 squared, which is 4. So 4k equals 1, and from there k must equal a quarter. Now that we know what k is, let's write out that probability generating function in full. So expanding the brackets, hope you can recognize this expansion. Multiply the quarter inside, and from there I can produce the probability distribution for the 3 outcomes, which are denoted by the powers. So I've got t to the power of 0, t to the power of 1, and t to the power of 2. And the coefficients are the probabilities. So 0 matches with a quarter, 1 matches with a half, and 2 matches with a quarter.